Hello, NEET aspirants. Let's solve a question from AIPMT 1994 question paper. An electron enters a region where magnetic field B and electric field E are mutually perpendicular. Then, option A, it will always move in the direction of B. Option B, it will always move in the direction of E. Option C, it always possesses circular motion. Option D, it can go undeflected. In this question, it is not given the direction in which the electron enters a region. Electron may be parallel to B or E or to both, or electron make an angle with B or E, etc. Now, if we examine the options, then option A to C are confirmative or assertive. Such statements should be true irrespective of the direction in which the electron enters in the region. However, option D states it can go undeflected. It implies that it may be true for a particular case. Therefore, option D is correct. We will discuss few cases related to the direction of electron entering in the region having fields B and E mutually perpendicular. For those who faces problem in finding the direction of magnetic force on moving electron using Fleming's left-hand rule. Video will be little bit longer. Let's examine certain cases. In case 1, electron enters a region parallel to the direction of electric field. We know that electric force on negatively charged electron is opposite to the direction of electric field, shown by white arrow in the figure and is named as Fe. To find the direction of magnetic force, we require the direction of a current. Conventional direction of a current is opposite to the direction of electron flow. Current direction is shown by downward blue arrow and named as I. In our diagram, magnetic field is perpendicular to the plane containing the electric field and going inside. The direction of a current I is perpendicular to the magnetic field. To find the direction of force by Fleming left-hand rule, stretch thumb, forefinger and middle finger of the left hand in mutually perpendicular directions. Point index finger in the direction of the magnetic field. In our case, it is pointing inside the plane. Point middle finger in the direction of a current. Then thumb shows the direction of force. In our case, it is going towards right, shown by white arrow and labeled as Fm, and is perpendicular to both electric and magnetic field. Electric force and magnetic force are perpendicular to each other. Now electron will be pushed down opposite to the direction of motion of electron. Its velocity is now reducing, while perpendicular magnetic force will cause circular motion with reducing orbit. Thus, electron will follow helical path somewhat. In case 2, electric field is along positive y-axis and magnetic field is along negative z-axis. Now electron is entering in the region of electric and magnetic field parallel to the direction of magnetic field, that is along negative z-axis. Electric force Fe on negatively charged electron will be opposite to the direction of electric field, that is along negative y-axis, and is perpendicular to the direction of flow of electron, shown by vertically downward white arrow labeled as Fe. Since electron flows parallel to the direction of magnetic field, angle between the direction of electron and the magnetic field is 0. From the equation, Fm, that is the magnetic force, equal to QVB sine theta. Here theta is 0, therefore magnetic force is 0. Only electric force acting perpendicular to the direction of electron flow, which provides a necessary centripetal force to move the electron in circular path in YZ plane. In case 3, electric field is along positive y-axis and magnetic field is along negative z-axis. Electron enters a region making angle theta with negative x-axis. Electric force on the electron will be opposite to the direction of electric field, that is along negative y-axis, shown by vertically downward white arrow labeled as Fe. Now Fe can be resolved along the direction of the electron, and that will be Fe parallel equal to Fe cos theta, shown by the arrow labeled as Fe parallel. Another component that will be perpendicular to the direction of electron, and that will be Fe perpendicular, which is equal to Fe sin theta, shown by white arrow Fe perpendicular. To find the direction of magnetic force, we need the direction of electric current. Conventional direction of a current is opposite to the direction of electron, shown by the blue arrow labeled as I. Direction of magnetic force can be determined using the Fleming's left-hand rule. As explained earlier, point index finger in the direction of magnetic field. In our case, it is pointing inside the plane. Point middle finger in the direction of a current, and the thumb shows the direction of magnetic force. In our case, it will be downward and perpendicular to the direction of a current, shown by downward yellow arrow labeled as Fm. If perpendicular component of electric field, that is, if Fe perpendicular is equal to Fm, the electron will continue to move on its original direction with acceleration due to the parallel component of electric field, that is Fe parallel. If Fe perpendicular is not equal to Fm, electron will deflected from its original path and will follow helical path, but not moving in the direction of E or B, neither it follows a circular path. In fourth case, electric field is along positive y-axis and magnetic field is along negative z-axis, or perpendicular to the plane containing the electric field and pointing inwards. Electron entering in the region along with the x-axis, thus the direction of electron, direction of magnetic field and direction of electric field are mutually perpendicular. Electric force is vertically downward, as negatively charged electron experiences a force opposite to the direction of electric field, shown by the vertically downward arrow labeled as Fe. Direction of a current is opposite to the direction of electron, shown by the blue arrow labeled as I. Now, by Fleming left-hand rule, point index finger in the direction of the magnetic field in our case is pointing inside the plane. The point middle finger in the direction of a current. Thus, thumb shows the direction of magnetic force. In our case, it is along the negative y-axis, shown by the yellow arrow labeled as Fm. Since both the forces Fm and Fe are in same direction and are perpendicular to the direction of electron velocity vector, provides a centripetal force to move the electron in circular path. In our case, it will move in a clockwise direction. Thus, electron not moving in the direction of E or B, nor goes undeflected. Now let's examine the case 5. We have changed the direction of electric field. Now it is along the negative y-axis. Direction of a magnetic field is kept as earlier. Electron enter in the region along the x-axis. Thus the direction of electron, direction of electric and magnetic field are mutually perpendicular. Now electron experiences an upward force along the positive y-axis, as negatively charged electron experiences a force in opposite to the direction of electric field, shown by vertically up white arrow labeled as Fe. Direction of a current is shown by the blue arrow labeled as I, and the direction of a magnetic force, according to the Fleming's left-hand rule, is vertically downward or along negative y-axis, shown by downward yellow arrow labeled as Fm. Thus, both the forces are along the y-axis but are in opposite direction. If electric force is equal to magnetic force, the electron will move on its original path without any deflection. But if Fe is not equal to Fm, or the electric force is not equal to the magnetic force, the electron will move in a circular path, as resultant force is perpendicular to the direction of electron. It will be clockwise or anti-clockwise, that depends upon the direction of a resultant force. Thus, electron may move deflected undeflected, follow a circular or helical path, or move opposite to the direction of electric field all depends upon the orientation of electric and magnetic field and as well as the angle through which the electron enters the field. Now, option A to C uses the word always. It means it should be true for all the cases, which is not so. However, option D, which states it can go undeflected. Here, word can is important. It implies that electron is going undeflected in certain cases. Thus, option D is correct. You may explore more cases by changing the direction of electric field, magnetic field, and orientation of electron. Like, share, comment, and subscribe our channel for neat solved questions. See you in next video. Stay tuned and stay focused.